In this video, let us try to solve some examples on bivariate probability density function so that we can understand the concept in a better way. Let us see some examples. First example, there are three pencils in a box which are numbered as 1, 2, 3. We need to draw two pencils at random without replacement. Only one pencil is drawn from each box at a time. Find the marginal distribution of x and y and also its CDFs fxy. So in the problem, they have given us a box which contains three pencils, and the pencils are numbered as 1, 2, 3. And we have to take a pencil. We have to draw two pencils from this box. So therefore, let us define two random variables. The first random variable be x, that is equal to set of 1, 2, 3, which represents the first pencil taken from the box. And the y is the second random variable. It is equal to 1, 2, 3. It represents the second pencil taken from the box. First, let us draw the joint PMF table fxy. Now, if I draw from the box, first, if I draw one, I can draw the second time. I can draw the second pencil, or next combination may be 1, 3, or next combination may be, if I draw 2 from first, then it can be 2, 1, second time it can be 3, or it can be 3, 1 and 3, 2. So possible outcomes are totally 6. Now let us look into the PMF table given here. When I draw the first pencil from the box, then there is no chance of drawing the first pencil second time. So therefore, it is 0. If I draw the second pencil first time, then I can draw the first numbered pencil second time. So if you look at that, I have here 2, 1, only 1 is occurred. So therefore, probability is 1 divided by 6. And if I draw the 3 numbered pencil first time, then I can also draw the 1 numbered pencil second time, that is 3, 1. So I have only 1 in this, so therefore it is 1 by 6. When I add these two, 1 by 6 plus 1 by 6, I get this as 2 by 6, that is 1 by 3, and this is known as marginal distribution of y at 1. Let us take the second row. When I draw the pencil numbered 1 for the first time, then I can draw the pencil number 2 second time. So that is 1, 2, and that combination is given here. It is only one outcome out of the possible 6 outcomes I have. So therefore it is 1 by 6. When I draw the 2 numbered pencils for the first time, then there is no chance of drawing the 2 numbered pencils second time. So therefore it is 0. When I draw the 3 numbered pencils for the first time, then I can draw the 2 numbered pencils for the second time. You can observe here. Therefore, it is 1 divided by 6. So when I add these two, I get this as 1 by 3. We'll go to the third row. So when x equal to 1, that is y equal to 3, that is 1, 3. You can see that I have this in this particular possible outcomes. So therefore it is 1 by 6. When x equal to 2, y equal to 3, I have 2, 3 here. So once again you can see that probability is 1 by 6. When x equal to 3, y equal to 3, it is 0. So when I add these two, I get this as 1 by 3. Similarly, let us calculate the marginal distribution of x by adding column wise. When I add column wise, 1 by 6 plus 1 by 6, I get it as 1 by 3. Here also I have 1 by 6 is 1 by 6, that is 1 by 3. Here I have 1 by 3 in the third column. So when I add all p-value x equal to x, that's the marginal distribution of x in each of these columns, when I add, I get this as 1. Similarly, when I add all the values under the column, the probability of y equal to y, I get this as 1. Now let us calculate fxy of x comma y. That is probability of x greater than or equal to 2, y greater than or equal to 2. It is the summation of x greater than or equal to 2, y greater than or equal to 2, fxy of x comma 1. So here if you observe, I have for x value greater than or equal to 2. That means I have to consider the 2 columns and with x value equal to 2 and x value equal to 3. Next I have y value greater than or equal to 2. So I have to consider 2 rows, that is the second row and the third row. So common values whatever I have here are 0, 1 by 6, 1 by 6 and 0. So when I add them all, I get this answer as 1 by 3. Let us consider the second example. Consider the following joint probability mass function, which is defined as fxy of x comma y is equal to xy squared divided by 30 for all values of s equal to x comma y, with f can take the value 1, 1, 1, 2, 2, 2. So remember here 2, 1 is missing. It is not defined. If x value is equal to 2, y value is equal to 1, is for this particular xy values, this equation is not valid. Show that the P of xy, which we have called it as fxy, is a valid joint probability mass function. What is the probability of x plus y less than or equal to 3? Third one, give the marginal probability mass functions of x and y, and what are the expected values of x and y? Are x and y are independent? These two, we will be looking into these two little later, but we'll solve in this particular problem. So given fxy of xy, that the joint probability mass function, xy squared divided by 13. Now we'll form the table for joint probability functions for x value taking 1 and 2, y value taking 1 and 2. Let us, we know that here it is not defined for x value 2 and y value 1, that is this. So therefore it is 0. When x value is 1, y value is 1 and x value is also 1, it is 1 divided by 13, what we get is 0.0769. When y value is equal to 2, x value is equal to 3. So we get this as this particular table, x value is equal to 1 y value is equal to 4, 2 square divided by 13. So that is 4 by 13. So when x value is equal to 2, y value is equal to 2, that is this particular square, we have here, it is 2 into 4 divided by 13, that is 8 by 13. From the table, it will be first what we have to show is this is a valid joint probability mass function. So this is valid because if you observe all these values, either it is 0 or positive. Therefore, we can say that fxy of x comma y is greater than or equal to 0 for all values of x taking 1, 2, y taking 1, 2. Second condition, we need to check whether the summation gives you 1. So here we have all, when we add all these 4 values, we should get this as 1. That is 0.0769 plus 0.3076 plus 0.6154 gives you 1. So since these two conditions are satisfied, we can say that fxy is a valid joint probability mass function. To solve the second part of the problem, for this we need to consider the table. The table, we had y values 1 and 2 and x values 1 and 2. And when I add x and y, I get 1 plus 1, 2, which is less than or equal to 3. So I need to consider the value of this table. Second side, that is 1 plus 2, that is 3. So therefore, x plus y is equal to 3. We need to consider this. And this is 2 plus 1 is 3. So we need to consider this. But this value should not be considered, as it is 2 plus 2, 4 is greater than 3. So therefore, you can see that probability of x plus y less than or equal to 3 is the probability mass function, joint probability, Pxy of 1, 1 plus Pxy of 1, 2 plus Pxy of 2, 1. That is 0.0769 plus 0.3076 plus 0. That gives you 0.3845. Third one, we need to find marginal probability mass function of x. So therefore, we have to find out Px of 1. Px of 1 are in the table. If you look at the table, we had the table. Once again, let me write the table. 1, 2, 1, 2. These are y values, these are x values. And if you observe here, I want for Px of 1. So therefore, I need to consider these two values. So therefore, I have Px of 1 is equal to sum of the Pxy of 1, 1 plus Pxy of 1, 2. That is 0.0769 plus 0.3076. That is equal to 0.3845. Next, we have probability, marginal probability mass function of x, actually, that is given by, and we need to consider these two values. So when I add those two values, I get this as probability mass function, joint probability of x, y of 2, 1, joint Pxy of 2, 2 will give me 0 plus 0.6154, that is equal to 0.6154. Let us try to find out marginal probability mass function of y. That is, if you consider the table, you need to consider these two values. This value and this value will give you Py of 1. So Py of 1 is 0.0769 plus 0, that is 0.0769. And probability mass function, marginal probability mass function of y at 2 is given by these two values you need to consider. So when we add those two values, we will get Py of 2. So we have here Pxy of 1, 2 plus Pxy of 2, 2 will give us 0.923. We'll consider the third one. We consider the figure given here. It has 6 regions defined as R1. That is the region So this is the region we are going to consider R1. Next region is R2, that is this region, and this region is going to be this is the region. Next we have got here R3, and the region here is defined by we are going to consider this region. Then we have R4 that is here, and it is given by this region. Then finally we have R5 and R6, and R5 is defined as this region. Then R6 is defined for the entire area inside this box. Let us consider each region one by one. The bivariate PDF is defined as 1 is for all values of x less than 0, x greater than 0, y less than 1, and it is 0 otherwise. So this is what they have considered for all values of y less than 1, for all x value greater than 0, this value is going to be 1. We need to find the CDF in all the 6 regions. We consider the first region, region 1. And in region 1, you can see that CDF is not defined for only value of x less than 0. So therefore, you can see that fxy is 0. So therefore, CDF is also 0. We'll consider the second region. The second region is this is the region. Now, in this region, let us consider a point. This is the point under consideration where y value is greater than 1 and x value varies from 0 to 1, anywhere between 0 to 1. So let us try to integrate the PDF in order to get the PDF. So fxy of x comma y, here x value varies from 0 to this point. So therefore 0 to x, integral of y value varies from 0 to 1, because only in this region CDF is defined. 0 to 1 and its value is 1. So when you integrate and substitute the values, we get this as x. Let us consider the next region, that is R3. Consider this as a point, and this point, if you observe, here the x value will vary because CDF is defined only for this region, 0 to 1. So x value will vary from 0 to 1, and here y value, that is here it varies from 0 to 1. So therefore, when you integrate this and substitute the values, you get this answer as 1. Our limit here is always included in the integrand. We consider the region R4. So this is the point under consideration. Here x value will vary from 0 to 1, whereas y will vary from 0 to y. So therefore, fxy is given by integral of 0 to y, integral of 0 to 1 du dt, that gives you y. We'll consider the next one, region R5. This is the region under consideration. We are considering a point here. And here you know that CDF is not defined. So therefore CDF is equal to 0. We consider the region 6, R6. So a point inside this square, and this point is in between 0 to 1. X u value will be between vary from 0 to x, and t value will vary between 0 to y. So the CDF is given by integral of 0 to y, integral of 0 to x 1 du dt, that gives you x y. We consider the next problem, fourth one. We have been given the bivariate CDF as these 4 points. The points are 0, 0, 1, 0, 1, 1 and 0, 1, and CDF values are given as 1 by 4. So therefore, bivariate CDF can be written as 1 over 4 delta x delta y from this point, 1 plus 1 by 4 delta x delta y minus 1 from this point, then plus 1 by 4 delta x minus 1 delta y minus 1 from this point, plus 1 by 4 delta x minus 1 delta y from this point. Let us consider now the 6 regions and try to evaluate the CDF in these 6 regions, R1 to R6. By integrating the CDF, we always get the CDF. For example, let us start with the region R1. Region R1 does not include any bivariate CDF value because x value is less than 0 and y value will vary from minus infinity to plus infinity. Since the CDF is 0, CDF is also equal to 0. Let us consider the next region, R4. In this region, if I consider a point, say this is the point under consideration, then I need to consider the region under this. And if you observe here, I have two CDF values, 1 by 4 and 1 by 4. So therefore, when I add them, 1 by 4 plus 1 by 4, you get the answer as 1 by 2. We consider the next region, R3, and this region is here. I am considering a point here. When I consider a point here, then I have to consider the entire region here. And when I consider this region, I will get all the 4 points under it. So therefore, it covers all the 4 points. So when I add them together, I get the answer as 1. So CDF at R3 is equal to 1. Let me consider region R4. This region R4 is there. So I'll consider a point in this region. Let me say this is the point. So now my region will include entire this. So if you observe here, it has two 1 by 4 values. So when I add them together, I get the answer as half. So therefore, CDF at R4 in the region R4 is always equal to half. Let me consider R5. This is the region, and this region always y value is less than 0. x can vary from minus infinity to plus infinity. Radius is not defined, so therefore the radius is also equal to 0. Finally, we'll consider a point in the region R6. Let me consider a point here, and if I close the area under that, this is the area I need to consider. It includes only one point. This is a point. So therefore, we can say that the CDF value is equal to 1 by 4. Thank you. In the next video, let us try to understand the meaning of expectations and independence with respect to bivariate random variables.